thank you very much for having us. It's a real pleasure to give a seminar today on the determination and the formal verification of the fifth Busy Beaver value. So it's work that was done mainly collaboratively at bbchallenge.org, which is an online collaborative research platform dedicated to this project, and May is one of the collaborators that will be talking with me today. But I also want to acknowledge the fact that this work was also funded when I was a PhD student through an ERC grant at Manus University, and through the companies that I created during my PhD, and heavily also subsidized by the French government. So thank you to all our sponsors, and let's get right into it.
Okay, I will switch to this thing and make sure that it's,
Yeah, so the Busy Beaver function, it was introduced in 1962 by Tibor Rado, and the definition goes as follows. It's a maximum number of steps done by a halting two-symbol Turing machine with n states starting from all 0 states. Well, it's technical, but the essence of it is really, I think, natural. The way my PhD supervisor described it was, it's maximum algorithmic bang for your buck. It means that if you have a budget of a number of states in the Turing machine that could be the same as number of characters in a Python program, you want to know what is the best program you can do on the metric of how long it's going to run before it halts. This function is uncomfortable because assume you had an algorithm to compute BBN, where you could solve the halting problem of any machine because you give me an n-state Turing machine. I run it for BBN plus 1 step, and if it hasn't halted by then you know that it will never halt. So somehow the number, they're able to predict the future. If you know BBN, you're able to solve the halting problem of all n-state machines. For instance, just to be clear, there are many models of what Turing machines are, and in this presentation, this example will show us exactly what we're talking about. We're talking about a Turing machine that has one bi-infinite memory tape, and you see how it goes. So we start in state A, so we study 5 states Turing machine, so you have 5 states, it's 1 row per state, A, B, C, D, E, and it goes as follows. So each time the machine reads something on the tape, so here it reads a 0, it's going to look at the instruction that it should execute at that moment. So 1RB means I'm going to write to 1, move to the right, and then look at instruction B. You can think of states as states a bit like functions, like function names in a programming language. So we can execute this machine. Okay. It runs, it does a bunch of stuff. And this particular one, after 11 steps, it's going to meet an undefined transition. It means that here it's going to be in state C, reading a 1. It's a transition for which we have not specified the behavior, and the machine will work. The question that comes naturally...
you can go back.
Yes, just weird. Okay. Question that comes naturally, so when you have a Turing machine like that, is to wonder, okay, but I can execute it, but will it ever reach an undefined transition? Maybe you're going to wait for a while, but you won't know if it will never reach one, if not hard, or if it will reach one, but in a very long amount of steps. Before our work, this was the state of the field. So before equals 107, which was found in the 80s by Allen Brady. It means that if I give you a 4-state Turing machine, you can know if it will halt or not just by running it for 107 steps. If you run one more, you know it will never halt. Yeah. The thing is that a natural question is how hard can it be in general, because a 4-state Turing machine is very small, but the answer is here. The idea is that any pi1 statement in logic, so it's any statement of the form for x, p of x with p, something computable, can be converted into a Turing machine. Actually, it's a one-to-one like association. And a famous example is with Goldbach conjecture. Goldbach's conjecture is one of the oldest open problems in mathematics, and it states that every positive integer n greater than 2 can be written as the sum of 2 primes. So what you can do is just enumerate all even numbers, and for each of them, try all the sums because it's bounded. You just need to check the primes below that, and maybe halt if one day you find a counterexample, so a number n that does not have this kind of representation. This has been done in practice. There is a 25-state Turing machine that halts if only if the Goldbach conjecture is false. It halts if it finds a counterexample. It was also verified in LIM, which is helpful because with this type of construction, it's good to have it formally verified rather than published anonymously with no documentation or comments, as it was done in this case. So it means that knowing BB25 is at least as hard as solving the Goldbach conjecture, because if you knew this value, well, you'd have a method to answer the question that Goldbach conjecture asks. Just run the machine for BB25 steps, and if it doesn't halt, you know the conjecture is true. There are other examples of pi1 statements, because it's actually a very expressive set of mathematical statements. Riemann hypothesis, it was shown by Matiasevich to be a pi1 statement, and it was converted by Aurier into a 144 state Turing machine. So this value is at least as hard as solving one of the most difficult problems in mathematics. You can go even further. The consistency of an axiomatic set, it's a pi1 statement because you can enumerate all proofs and until you find a proof of a contradiction, 0 equal 1. And this was done in the case of ZF with quite a small amount of steps. So this shows that not only the Busy Beaver function is uncomputable, but even if you try really hard to find some values, you're going to hit some walls that are really hard, such as like the Riemann hypothesis or the consistency of ZF. There is a conjecture that even BB10 is independent of PN. So in the 1990s, if we go back to the field Busy Beaver number, in 1989, Martin and Buntrock, two German scientists, they discovered the 5-state Turing machine that halts after 47,176,870 steps, which was the best thing that was ever done in history. Actually, there were contests organized in the 80s in German universities to try to find a good 5-state Turing machine. And it's a few years later that they found what became the champion. So this is what it looks like. This image, how it works, is each line is a successive tape of the Turing machine. So no, it doesn't say much other than, okay, it's doing stuff. Here it's only 20,000 steps, but to have a complete image, you'd have to run it for 47 minutes. The thing that's interesting, and that was very inspiring for our project, is that in 2003, there is a pioneer called Georgi Georgiev, which is a Bulgarian scientist that goes under the nickname of Skelet, apparently because he was always very thin. And he published an online program called BBFind. It consists, it claims to be able to understand the behavior, to decide the behavior of all 5-state Turing machines apart from a small list of 150. It was the best result the field had since 1989. The issue is that it consists of, it's still available online, we post it on our website also. It consists of around 6,000 lines of uncommented Pascal. And so that comes with concerns about the correctness, because how sure can you be that there were no bugs, etc. Importantly, it failed to find a better machine. So that led a few years ago, in 2020, Scott Aronson, computer scientist, conjectured, he stick his neck out and actually conjectured that since it's been so long that we didn't find a better machine, this must be the one, and the machine of Martin and Buntrock is actually the winner. This is how BB Challenge came alive. It was actually to prove this conjecture. So this is the work that we've done, and it was the final proof, which has been written in code, was released in July of this year. We proved that this equality means that you cannot do any better. So for each machine with 5 states, you need to prove that either it had before this number of steps, either it never had. I created that platform in 2022, and it consisted of online collaborative research. So I think something interesting is that there was no kind of management. It was really anthropic, so people would come organically and do stuff and generally advance the state of the progress. And even the formal proof, the Coq formal proof, it came by chance. It was not an objective at first. even it was a dream of mine. I thought maybe in 5 to 10 years we'll be able to have this done in code, but at first, let's not even try, it's going to be too hard. But it's collaborators that came up organically to the project like me that brought the first elements of the code proofs, and then that were also implemented by other contributors. Today we have around 800 members on this online community, and around 50 active contributors, people that often post messages and work on the problem, and 15 contributors whose contribution ended up being used by the code proof. It's decentralized in the sense that everyone has their own repository with code doing stuff, and it uses every language you can think of. So there was no constraint that people should comply to use this or that language. And now we're going to talk about a general outline of this proof, and they're going to tell you later.
Okay, so the general way you prove concrete Busy Beaver value is you like enumerate all the Turing machines, and that's actually where you find the first obstacle. Because if you do look at this like combinatorically, you calculate that like, oh, there's probably about like 10 to the 13th possible 5-state Turing machines, and when you see like scientific notation, that's like a good first hint that you probably don't want to like actually iterate to everything. And it turns out that there is like a lot of symmetries and pruning you can use here, and that like knocks you down by 5 orders of magnitude. So you have like around 200 million Turing machines. What do you do with that? Well, clearly you need to write some kind of programs to sort them for you. So you have like automated proof strategies. We call them deciders, which is like programs that like take a Turing machine and like try to come up with like facts about it, and either they output that it holds, either it doesn't hold, or they go like I have no idea about the Turing machine, or they report unknown. And the last possibility is why it's possible to write a program language in the first place, because otherwise it's like proven impossible, because like this is literally solving the halting problem. And if we get the unknown verdicts from one decider, we try another one, and we form this pipeline of like successively more advanced, or rather more tailored to the leftover set algorithms for like attempting to decide Turing machines. And in the end, yes, and all this is like the crux of the proof, where you want to have a formal proof of correctness for these algorithms, which like you generate stuff like, well, if the decider says that it doesn't hold, then it doesn't hold. And after we run our pipeline, we get, I think it is 13 machines that didn't work, that no automated strategy could deal with. And we call them holdouts. And these are usually the machines with the most interesting behavior, and because of that they are interesting to study. Okay, so let's look a bit closer about each of these 3 parts. First, we have the Turing machine enumeration. This like solves 2 problems. Firstly, you can have equivalent Turing machines by just renaming the states. For example, here I swapped C and D. So here we have it goes to C, here it goes to D, and like this is clearly gonna behave the same. You can like formally prove like like this is basically an isomorphism. The second issue that we need to deal with is that the machines can differ in parts of their code that are like entirely unreachable. For example, if we take this machine with like 5 undefined transitions, it turns out that it never reaches any of those undefined transitions. So whatever we put in there, the machine still isn't gonna halt. And you really don't want to be looking at each of those individually, because they are all the same. And the solution to this problem was first suggested by Alan Brady with is it like BB4?
Yeah.
Yeah.
No, even before that, he was working in competition to solve BB3 with another team. Well, the other team won, but he introduced the algorithm of that one in his PhD thesis.
And the solution here is like very simple to state. You enumerate the Turing machines as you go, and you choose the like what should a particular transition actually be when the Turing machine actually reaches it. So let's look at how that looks in practice. We start with this Turing machine with the 1RB transition in the upper left corner. You can actually prove that like that's the only interesting one to start with out of all the options, but we won't get into the why. And then you execute the machine, and well, after one step, because the B state is all undefined, so it holds. So then you take all the options for that new transition. And the thing about this is that you have the A state and the B state, which are like mentioned in the transitions table already. Here's the B, and A is the start state. But C, D, and E are all equivalent. So we take the first undefined, completely undefined state, and we choose. We go through these options, and you get like multiple options. One where the new transitions is 0 LA, then you have 1 LA, 0 RA, and it's like there's like 12 of them in this case. And then you give all of those to your decider pipeline. And of course, you have here only 2 real states, so this is going to be quite easy to solve. And your decider pipeline was like, oh, these halts, these don't. And if they don't, like all Turing machines where these undefined transitions here are defined, you can consider like doesn't hold. And for those that do hold, again, let's pick one of those. You see where exactly it holds. It turns out it's this transition. So you fill them out, and this is like rinse and repeat. You give them all to your decider pipeline, and you repeat this process, creating this kind of tree, such that you in the end get to like the last undefined transition. And if if you fill that out, you remove any possibility of the machine's halting. So that's where the tree cuts itself off. The thing to note here is that the TNF enumeration is like unreasonably effective because if you divide out by all the maybe I should do it so that the Zoom guys also can see it. If you take into account like all the symmetries where you can swap left and right, you can you can permute the names of the states. This gives you like back of the envelope. It should get you to like around 10 to the 11th. And actually what you get is like 10 to the 8th. So like three orders of magnitude better than expected. And this is like actually one like loose end. Like it would be interesting to like do some more accurate combinatorics on this and see why this happens. So let's do part 2. We have all these machines. How do we even attempt to like solve the halting problem? Like this is in general impossible to solve by definition. So the strategy here is that we want programs that are good at one specific thing, and solve a big fraction of the remaining machines. So that we like don't have to do that many deciders. So here we have some statistics, like from the total of 180 million machines. almost all of them are decided by the first decider, which detects loops, and we have more advanced techniques, and it's a quick drop-off, right? So yes, the first possible idea when you try to come up like with proving that the Turing machine doesn't help is like there's got to be some machines that just like enter a cycle, right? And here's one example. We can run it for like a few steps. And you notice like, hey, here the tape is the same, the state it's in is also the same. So if we keep it running, it's gonna be repeating the same pattern forever. And this is like very simple to code up. You can do like a simple hash map based solution. You can get a bit fancy, implement Floyd's tortoise and hare. There's an entire Wikipedia page on this. But let's get a little bit more complicated. So for example, this machine, it also cycles, except the pattern that it does is like it's slightly shifted on the tape. So let's say, well, okay, we will compare the tapes like relative to the position of the Turing machine's head instead of like an absolute, and then these are like the same tapes, so our algorithm works. But then you realize that you are actually solving a special case here, because there are other machines where they don't actually leave the tape behind that's like clean. So that is like you need to think about this for a moment. But the key observation here is that if I have like one cycle, the Turing machine never actually goes like beyond this point. If I have this part, the tape head doesn't go beyond this point. And because of that, we only have to compare this part of the tape, and we get to ignore this part. And this is also like relatively easy to write an algorithm for. And this was first presented in like the 1960s, and it was used for the BB of 3. If I remember correctly, BB of 2 can be like fully solved with like just this decider. And there is, however, like one very surprising and very neat fact that we have discovered quite recently for how to approach these machines. Specifically, this is a metaphor that Sean Ligotsky came up with, if I remember correctly. Is that imagine that your Turing machine is like a physical object with a mechanical implementation. And imagine that each transition in the transition table that it does, like each of those makes like a slightly different mechanical noise. So if you listen to it for a while, you can like discern it. And the amazing thing here is that if you just listen to that, you just look at which transitions that the Turing machine is going through, without looking at what it does on the tape at all, that's enough to prove that the machine entered a cycle if you get like a twice repeating section of the sequence. Now, side conditions apply, like about the length and about like where the machine is on the tape. You can say that a few equivalent ways, but this is the general idea, and I think it's a very surprising and beautiful fact. And I will like we have this theory that this was actually quite important for the Koch proof, because there is a lot of cyclers and a lot of translated cyclers. So a bunch of computation needs to be done here. And this algorithm is much more memory efficient because it doesn't need to store the tape. And the translated cycler family is quite a varied family. For example, here we have behavior that only starts about 1,000 steps in. In fact, they can get a lot bigger. One of the holdouts actually turns out to be a translated cycler. The translated cycling behavior starts after 10 to the 51 steps. We had to write an accelerated simulator that was tailored to this specific machine to get it that far. It is one of the most complex Turing machines. And you will note that we call it skeleton number 1. This is because the author of the BB-Find program, skeleton, released a list of the machines that his program couldn't decide. The list was split up into about 100 machines. He just I looked at them manually and they're easy. And then there were the hard ones, 43 of them. So we have skeleton 1 through skeleton 43. Our algorithms solve some of those, but all of our leftover machines were already identified by skeleton. Okay, but the translated cyclers is quite an easy family if you think about it. You could say yeah, that's the easy part. The rest is probably impossibly hard. But you have two strategies to continue from there. You can identify specific classes of behavior and then write deciders that are tailored to them. And this is what we did for the bouncers class, even though it didn't end up being useful for the final BB of 5 proof. Or you can try to write a generic method that approximates the behavior in some way. And this is a form of abstract interpretation, which is quite a recurring concept. It's an entire subfield of computer science. And one of the methods that we would just like to give you an idea for is the n-gram closed position set. And this is a big name, but it's the main idea is relatively simple. Specifically, we take the execution state. We have the tape head and the tape, and we say that we will only keep track of a local vicinity of the tape. Here we have the n equals 3 in this example, so we remember the 3 tape slots to the left and 3 tape slots to the right. Well, then you might say okay, how do you execute that? Because you make a step, and then you need to update this vicinity somehow. How do you determine this? And this is where the n-grams come in. Let's take the example, the state of the tape from the example, specifically its right-hand part. And here are all the length-free sections of it. And these are the n-grams. And this is how we will, and we will keep a set of these n-grams, which is our approximation of what our let's say statistic model, even though there's no statistics involved, approximation for how the tape could look. But this approximation, importantly, is sound. And here, if we take a look at this, we see that the known part of our tape starts with a 1 and then a 0. So we look through our set, and then we see maybe I shouldn't be drawing with the mouse here. I have a proper stylus. We're looking at this, and then we see all the n-grams we have. Obviously, in an actual set, there would be 1 copy. All the n-grams start with a 1 and then a 0. like all of those have a 1 at the end here. So therefore, we can say that this must be a 1. Of course, we're not always that lucky. For example, if we try to determine this, we need to look for n-grams that start with 0 and 1. And here we have 0, 1, 0, and we have 0, 1, 1. So here the execution splits non-deterministically. So we have this set of local configurations and this set of n-grams. Well, we can't actually determine the set of n-grams by looking at the tape like this, because we aren't actually executing the Turing machine. So we need to build it as we go with like, or we're running away. We're going to discard this, so we add this to the n-gram set. And we run this to a fixed point, and we hope that at some point the set will stop growing, and that we will not, and that our abstract interpretation of the Turing machine will not reach the halting transition. And this is the general idea, although there are like details that make this more effective. Okay, yeah.
Yeah, and as we see, as May said, because we're not trying to track one particular behavior, but just approximate the behavior with this kind of statistical method in this case, the type of machine we can decide, they don't necessarily need to have something in common. Here, for instance, on the left, you have something, this is done by a 5-state machine, it's kind of a fractally loop that you could spend hours trying to decipher and give a formula for. On the right-hand side, you have something that look really messed up, that looks to be somehow counting in some bases, but with high degree of obfuscation on the digits or something. But both are solved by the same abstract interpretation. Something I really liked about this method also is, in our case, it features a great deal of collaboration, because the word CPS, so it was first reverse engineered from the code that dates back from 2003 by one of our collaborators that studied the code and figured out a method that's more general than this. Another contributor tailored it to something simpler using the n-gram abstraction, but it was simpler but couldn't solve that many machines. And the author of the main coq proof, coq-defined that we're going to talk after, used this idea and made it more general by using a very simple trick, saying, yeah, well, instead of just having zeros and one on the tape, we're going to augment the alphabet to remember on each cell what was the path at the fixed length history, for example. So we're going to look at n-grams, but in an augmented alphabet, and that method turned out to be crazy effective on the hard machines that were left in the pipeline. So where are we at? Here we discuss loops, this method, n-grams close position set. You can see that together they decide 99.99% of the machines. But of course, the hard machine comes when you go down. Some other techniques were developed, but something that's really nice is that all the ones circled in blue, they can fit in an abstract framework that reduces the behavior of the machine to a finite state automata. So it's along the line of what May said, it is approximating the set of configuration reached by the machine in a bigger set. So we are overestimating what are the possibilities seen by the machine, but we do that with a regular language, which is easier to work with and show that it's closed and does not contain any halting configuration. We also have one method that pushes this idea to an irregular model of computation, so past finite state automaton, using weighted finite state automaton. But in the end, you're still left pretty much with 13 machines that prove to be extremely hard.
Yes, and a common theme in the irregular machines was that they were doing some sort of counting, like 2 different counters on the tape. And, well, at least our proof for these machines relies on the invariant that the counters are in sync somehow. And I think this is nice because it's kind of an analogy with a common example of an irregular language. Namely, you have the like a language like this, where the exponents here have to be the same. This is like the first example of an irregular language that you would have in an automata course. I should clear this. So let's look at the holdouts, at the so-called most interesting machines. One machine that I really like is similar in spirit to those irregular machines that are still solved with some of the most advanced deciders. Except instead of doing the counting in any traditional base, it does it in like base Fibonacci. And this is a neat small, I don't know how well known fact in like mathematics, that you don't need a bunch of like abstract stuff to prove. Specifically, if you take the Fibonacci sequence, which is like defined by each number in the sequence being the sum of the two previous ones. If you take the sequence, then every natural number can be written down as a sum of Fibonacci numbers in exactly one way, provided that you forbid using the like immediately adjacent numbers from the sequence. And here we have one example, like 17 can be written as 13 plus 3 plus 1. Actually, there is a neat algorithm for finding these representations, which is like you take greedy from like the biggest and you could go down. And the skeleton number 10 machine counts using like two representations that correspond to base Fibonacci. And it's to me, it's really surprising that with 5 states of a Turing machine, you find this example. And this shows like how this research is kind of similar to biology, and that you don't write the programs, you start looking for them, and then like deep in the sea, after you've like gone like a lot down by writing out of deciders to filter out the less interesting things, you find these gems. Other holdouts include the skeleton number 1, which, as we've discussed, like it takes it has like a 10 to the 51 state, the 10 to the 51 step warm-up periods where it's just like pure chaos, and we needed like four layers of abstraction in the, or like 4 layers of acceleration, and we didn't know until the very end if this will ever it will ever be enough to like make sense of the Turing machine. Another interesting one is skeleton number 17. And it's like a relatively complex problem that involves counting in gray code. Especially, there are like lists of numbers, and the parity of each number is like interpreted as a gray code, and then the rest of the numbers, so like the bits like above the least significant bits, they are like involved some other way. And this was complex enough that it has its own paper on the archive. Yeah, so let's talk a bit more about the formal proof specifically. And yes, initially, like this was a fever dream. Like nobody in the project realistically thought that this is the right way to go. So like how do you ensure correctness in such a context? The idea was to have like very modular pipeline for everything, and for each component have like independent implementations by multiple different people, and make sure that they all agree. This meant that the enumeration. Like it couldn't like just ask the decider pipeline because we didn't want to have like tight coupling between these components. So it used a very simple criterion, like run it for the conjectured number of steps. If it holds, then it holds. If it doesn't, mark it down as undecided. And this meant that it had like, this is like a quite computationally intensive approach, because the trade-off is like less thinking for us, more thinking for the computers. And because of that, it took like, what, 30 hours to compute this at first, and that's like spread out over 10 separate computers. But over time, we kind of started making steps towards formal verification. In 2022, Nathan Fenner wrote like formally verified versions of like some of the deciders. He used Daphne, and then at some point I joined the project. Maybe a little bit about how I ended up there. Like formal verification, like it's a very appealing concept to like be able to have the computer say that yes, what you just did is correct, and I am the kind of person who like really likes their correctness and really wants to be sure that what I am doing is like there are no mistakes in it. And like at first I started with Isabel because I found the logic easier to understand at the time. Like when I was supposed to be like paying attention in literature class in high school, I instead was reading certified programming with dependent types. And I got a few lessons from there that you can find in the code base of today. And then there came a time where I found myself to be quite burnt out from my job, and I wanted to take a breather. And as like vacation, I did like I did the software foundations course. It's a really good way to learn Coq, in my opinion. One of their exercises is, oh, here's like an example algorithm for matching regular expressions. Try to prove it correct, won't you? And it was like a neat exercise, but soon I wanted to be doing real things and not exercises. And then I remember like having heard about the Busy Beaver problem from like some popular science video, and I decided to like look it up through the online encyclopedia of integer sequences, and I found my way into the project. And here I started first like the simple deciders like translated cyclers. And then I set my sight on the holdouts, and this was actually the first good the first use case where Coq could shine, because the thing is that if you have an algorithm for the decider, like it's like they are invented by us, they are supposed to make sense. So it's relatively easy to like convince yourself of the correctness of the algorithms. But if you have individual proofs for Turing machines, it's often you're trying to like make sense of some chaos, and that is the kind of thing that is easy to make a mistake in. In fact, when the skeleton #1 work was first done, the community, like the blog post that announced it was, skeleton 1 doesn't halt. We think. We are not confident that we didn't make a mistake. But it turns out that they didn't, because at some point I decided to tackle that part, and I wrote a proof for skeleton #1. And this is where others started paying attention, and some people in the project decided that they want to learn Coq to some extent to be able to tackle some of the other holdouts. Yes, and the thing about proving holdouts is that it requires a lot of work. There's often moments where you are following like an informal pen and paper proof, and you have like 2 lines running, oh, this little inequality, and then you spend like an entire day or two trying to like screens of code trying to translate all that reasoning that was compactly presented in the inequality. And because of this, my motivation dwindled and progress on the code proof slowed.
But something very surprising happened, something that, again, happened in the context of a collaborative project where everyone could join. In April of last year, someone that had never talked on our community, called MXDYS, joined and said, I've solved the problem, here's the code proof. Well, it was almost solved, like their proof, I think, had 20 or so holdouts.
I think it was like about 80.
80, okay. But by talking with us and improving on using, finding what we had done that could be applied directly, such as the holdout proof that may have made in code, they eventually come up with solving everything but one machine, scale 17, and 1 month later, they had solved it in a proof, which is actually different from the one that was published on the archive. Yeah, it really blew my mind personally, that someone also, I think they did it in a really small amount of time, maybe 1 month or 2, something like that. And where it really pays tribute to collaboration is that they saw everything we had done, implemented it in code, in some places made it better, and then interacted with us to just cross the finish line. So the code proof really relies on the contribution of at least 15 people. But when I mean really relies, that those people invented or developed the concept that end up being used in the proof. The proof initially compiled in 10 to 13 hours, but thanks to help from the core team in Paris, we were able to first use a faster computing engine in code that's called native compute that goes faster. And then May mentioned that the proof basically builds a tree of Turing machines. And it's very easy to parallelize a proof that does work on trees because you can just break subtrees in different independent files and compile those files in parallel. So actually, there's no limit today to get this time down to even 10 minutes or lower if you have enough cores. It's just that it's a bit tedious because it's done manually at the minute. We also made an extraction because the proof initially was not accusing any information, and at the end of the day, what we really care about is to have a list with all 5 state Turing machines that was enumerated, and for each, does it halt or not, and what is the technique that was used. And so just by inserting print statement thanks to the OCaml extraction, we're able to generate this file, which is literally a verified enumeration of the space of 5 state Turing machines. So I just wanted, we don't have much time left, but I wanted to, wanted to give you just a glimpse of information about the coq proof. So the coq is on GitHub. All the concepts that we have talked about, you can find the names in this folder structure, like deciders. But if we click here, we have a folder with the implementation of all the deciders. So each of these files contains the implementation of the algorithm and the lemma that says the implementation is correct. And you also have the TNF enumeration. So in all the files that mention TNF, they actually do that. And we have tried to do good practices where we have isolated the statement of the theorem in a file that's quite transparent and only 120 lines on the whole 50,000 lines that the proof takes. And you can see that, for instance, just the definition of a Turing machine is very transparent, where we say a Turing machine, it takes a state as input, a symbol, and it will reply a transition or none if it's not defined. And the statement per se, it's written here, it's saying that for all Turing machine, if it halts at time step n0, then n0 is less or equal to BB5. And there exists a machine that achieves that bound. And when you go to the theorem file, that works a bit like the entry point of a huge program. I really want to convey the idea that this project is closer to software engineering than traditional, I'd say, mathematical proofs. At least me, for instance, I had no idea about the world of formal verification beforehand, and I was really surprised to see those two worlds of mathematics and computer science kind of collide in a beautiful way. And you can see that the theorem itself, you have a proof for the lower bound. That's the easy part, because you just give the machine that achieves the lower bound. And then you have a proof for the upper bound, which here is an entry point for a big rabbit hole that does everything that we just talked about. And then finally, sorry. To go very quickly, when you compile it, it will tell you the assumption that it's used. So you can see that in 36 minutes, it enumerates all Turing machines, run all the algorithm on them, and agrees that it transfers the right value of the field Busy Beaver number. It uses one axiom, which is functional extensionality depth, which basically says that two functions are the same if they agree on all their parameters. It is actually not using this axiom could be possible, but would require a lot of refactoring.
Yeah, this is because the representation of the tape that is used is a function, and you really often want to say like these tapes are the same.
Yeah, and as a final sort of landscape, here, this table on our wiki pages, we show the landscape of small Busy Beaver values. So what we've done is that we've proved two new values. Something we've not talked about is that you can generalize the notion of the Busy Beaver number to Turing machines that use more than 2 symbols. In theory, you can do more if you use 3 or 4 symbols. We've proved a new value that was not known. And out of completeness, we've given core proofs that are different than the original one, actually, for all the values before. So you could ask, okay, what's next? Is it BB6? Well, first bad news, BB6 is bigger than 10 to the 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 10 15 times. So 10 tetrahedron 15. And this was discovered by the same people that accelerated Skelet 1 to be able to discover that it does stuff in a huge amount of time. Because with accelerated simulation, of course, you're not going to simulate this step by step, you're able to show that the machine had after a tetrahedral amount of steps. So first, we are a bit doomed. And then it's even worse because we have found a 6-state Turing machine whose halting problem is equivalent to something that's very reminiscent of the collapse conjecture. It iterates a collapse-like function from a starting point, and it asks, do you ever get twice as many more odd terms than even terms? If we just put it mathematically, it says this. And this is I'm really happy about, because this was one of my motivations studying the Busy Beaver problem, was trying to find the smallest open problem in mathematics on the Busy Beaver scale. And we've shown that it's not with 5-state Turing machine because we can decide them all, but with 6 states, we have problems that will probably require breakthrough in mathematics, or maybe are independent of common axioms to be solved. So this particular machine, no one on Earth knows if it transforms. Something quite funny is that everyone that worked on BBN said that you could not solve BBN possible. And they wrote it, which is even cooler.
Yeah, we call it the Busy Beaver lack of hope recurrence.
Yeah, so exactly. So in the 1960s, the people that work on BB2 said, no, BB3, forget BB4 even. And it repeated again, BB4 to BB5, the author that solved BB4 made a prediction. Actually, there's another screenshot that's better than this one. You just write prediction. We will never know the value of BB. So to end on a hopeful note, I say we'll never know the value of BB6. And thank you very much for having us, and we'll be happy to answer questions as well.
bit of an esoteric question now, but the last slide you showed with we will not know was Brady or something was his name, and I saw he died in 2024. Was he alive still when you did it?
Yeah, like this is actually quite a sad, sad point. I believe he died like
4 days.
Really.
4 to 5 days before the proof wasn't.
Oh.
Yeah, so he didn't get to hear the great news.
But did he hear that you were close, or?
I don't think.
Oh,
Yeah, I don't think anyone has thought to message them until we have actually did it.
Yeah.
And then we have found that we just missed the time.
But we didn't know we were close also. So
Yeah.
it just dropped like a bomb. But, I mean, the proof arrived out of space. Like we did not expect it. So I mean,
Yes,
Martin died just a few days after MXDYS first announced the first proofs.
Yes, but before MXDIOS came around, the consensus-based approach was at around, if I remember correctly, 2,833 machines left over to deal with. So it was quite a big jump.
Yeah.
No, I just want to thank you for the great talk and congratulations for doing that.
Is there exactly one machine that holds after BB5 steps, or
I think yes.
Yeah, I think that's the biggest, and the second biggest is around 20 million, something like that.
so up to trivial naming of states?
Yeah, exactly. Yeah. And actually, it does. Some people have studied the machine closer, other than saying just it halts, and they've shown that it does simulate a collapse-like function, but the one with a trajectory that does.
Yeah, it gets lucky where it like iterates it shows like an initial value and a specific function that happens to have like many like the most amounts of terms before reaching zero or whatever the halting condition is.
Yeah, and I would say also it's important. It's not because we've decided the machine that we've understood them. For most of them, when you use something abstract like n-gram CPS, you don't understand the machine. You find it doesn't halt for irrelevant reasons in some sense. So there's still a bunch of questions you could ask. For instance, just how many different ways 5-state Turing machine can count. We've seen crazy things like Fibonacci bases, but there are also machines that count on one side of the tape in base 2, on the other side in base 3. You really have a really rich environment of weirdness.
Yes, one thing that I think is like would be quite hopeless is generalizing the problem. Like instead of having on all zero tapes, you want to like have the tape be an input, and deciding that like for that you would probably have to understand each machine, and that feels quite hopeless.
Do you think that studying BB6 could give insights into the collapse protection?
Well, maybe another way. Studying BB6 is a reason to, like is basically a ploy to get people to care about the collapse conjecture, which like
it shows that those problems. Often when you hear about the collapse conjecture, people say, yeah, it's an isolated part of mathematics, it's connected to nothing. Okay. But we see that in computation, actually, and Turing machine are not the only instance, small computing engines very often are quickly able to do collapse type stuff. So, and we know also that generalized collapse maps, so if you don't limit yourself to 2 maps, but n maps, they are able to be trained complete. So there's something like interesting there in the connection between theory of computation and collapse-like function. So,
yeah, and maybe you find some similar functions for which you can actually prove something and can then translate that back to collapse.
Yeah, I think the state of the art is either it's you can prove everything you want for very trivial reasons, or it's like very, very hard.
Or you have obvious arguments. It's also something that have been developed a lot in our community. I think the word comes from Conway. It's to say it obviously has or doesn't have for probability reasons. So if you model your collapse sequence like a biased random walk, you can do some analysis. And I think anti-Hydra obviously doesn't have.
Yeah, it obviously doesn't hold because it gets like further and further away from possibly halting. And if it was a truly random sequence, then that would be a correct proof. But it's not a truly random sequence. It is like defined mathematically. It's only pseudo-random. So who knows? Maybe it's so we do not have the techniques to be able to make like airtight statements about these.
It's already 5 parts, so maybe we can have your question as the last question.
Yeah, it's a bit of a practical question how you go about analyzing these machines. Is it that you try to, people try to come up with Turing machines for existing problems, right? So do you try to match these machines with the ones that people invented, or do you try to analyze them?
Yeah, I say there are two approaches. What you're describing is really top to bottom. So I take an existing problem and I try to condense it into the smallest machines that can do it.
Yeah.
But it's exactly the opposite. You go hunting for a machine in nature and you find stuff that does not relate to most of the time does not relate to stuff that we naturally come up with. So you end up with techniques that actually say, okay, let's forget about what the machine does and let's try to just build a net that's coarse enough to catch some fish. And so
like the general way you analyze an individual machine is like maybe you try to simulate it and try to find patterns in that.
Yeah,
you can have like, okay, let's take like this example tape and manually reason through how it goes through this. And as you do that, you can come up with like, okay, lemma, if it's in this state and it has like this repeating part and it goes through this repeating part this way, and then you go like, hey, hold on, this looks a bit like the rules for counting, or like, hold on, this looks like that. And you basically brainstorm with others and like, hey, do you see something interesting here?
Every collaborator will have a different answer. So that's the cool part about collaborating.